Hello, welcome back. Today we are going to talk about the error of the output. Okay? Imagine we have a neural network that ends up with this layer that has some inputs, and we have 4 outputs. If we want to train our neural network, the first step is to compare our output vector with the label that is the result that we would have to output. So the first thing to do to compare it is to calculate the error. There are a few ways to calculate the error of the output to recompute our parameters and weights in order to learn. So in this tutorial we are going to see the MSE error and the cross-entropy. Okay. The MSE is also called the mean square error. Mean square error. And there is also another variant of this type that is called the absolute square error. So firstly we are going to talk about the MSE, the mean square error. The mean square error is given by this formula. MSE is equal to 1 divided by n, and n denotes the number of outputs of our neural network, and now the sum of our predicted value y minus the real value that we had to output and square. The difference between the mean square and the mean absolute error is that instead of multiplying by itself, we write the absolute sign. So the square function here is to only write the positive value in order to have a mean square that represents the real error. And there are also people that want to write a number 2 here to simplify the derivative after. So now we can do the derivative of our mean square error. The derivative will help us to do the learning process of our neural network. So the derivative of our mean square error with respect to our output, you have to care about this notation. Okay, the output is this. Okay, so this would be 1 divided by 2 by n, and now we are doing the derivative with respect to y. So we will only care about one of these summation. So we do the derivative of our square, that would be multiplied by 2, and now we only have to write this the same, minus y, and we simplify this by this, and we get that the derivative of the MSE with respect to one value is this. This would be the formula of the derivative. So when we are doing when we are working in a vector, imagine we have a vector that this is the vector y hat, our output, and this is the real vector. So what we are going to do is we are going to do the difference between those vectors, and this would be the derivative of the MSE with respect to each one. So that would be the result of our derivative. Now we have finished this error, so we can turn with the cross-entropy. So now let's talk about the cross-entropy. Cross-entropy error. The cross-entropy. You have to care about the origins of this word. This word is usually used in physics, and we have extrapolated this into other fields like machine learning in this case. It's a way to measure the distance between two vectors in this case. So to measure the cross-entropy we need first the y hat, our output, and then the labels that we should have the labels that corresponds to each output. So it is given by this formula, the sum of our y log of y hat. This is the formula for the cross-entropy. You have to notice that this formula is not symmetric. And what does it mean? That you have to write this in order. First the output and then the label data. Now we have given this formula, we have to see the loss function of this function. So the loss function would be 1 divided by the number of outputs, like we have seen in the MSE error. We have to divide by the number of outputs to do the mean. So you have to care that cross-entropy is only used for probabilities in this case. So it should go through 0 to 1. The label data should be 0 or 1, and our output would be between 0 and 1. Imagine we have this is our output, and we have a probability here of 0.7, 0.2 and 0.35. and our label data should be 1, 0, 1. So now we can compute the cross-entropy function because we have matched the rules for doing that. And now we have to do the derivative. So as you know, we will notate this as the loss function that is the literature of in machine learning. So when we are doing the derivative of the loss function with respect to our output, we have to do minus, because of this minus, and we multiply y, our target, okay, divided by y hat. And why are we doing that? Because the derivative of the logarithm is 1 divided by what is inside, and we multiply that by 1, so that's the result. So when we are imagine we have a vector that is the output and a vector that is the label data that we should have output. So what we have to do here is here when we are doing the derivative of this with respect to y hat, this would be a wise operation, an element wise operation. And what is that? That we multiply each value, we do an operation of each value by each value. So first our I1 divided by I hat 1 minus I2 divided by I hat 2, and that to the end. So now we can code it by ourselves. So we open Visual Studio, we go to the output file, and we start coding it. So the first thing that we need to do is include the eigen library, the exception library that exception, and our configuration config. And now we can create the output class. This class would be the base class, and we are going to inherit it from this class, protected. We create our type def, firstly the matrix, scalar, eigen dynamic, and we are going to call this matrix. Type def eigen matrix scalar eigen dynamic, and this would be the vector, so size 1 vector. And we also have to care about this one, the eigenrow. This would be a row vector of dynamic size and y. This means that it has to be an integer vector. We have to it has to be an integer vector because we have talked that before, that in the cross entropy we need to do with probabilities with that has to be 0 or 1. So now we can implement the different functions. First one, the virtual constructor, output, the virtual void evaluate, that we will give as input the previous layer data, the output, the white hat that we have talked before, and we also going to have the matrix. One moment. Okay, the target data. Virtual void, and we are going to do another function that this is going to be another one moment. This is going to be another implementation. Oh, sorry, I forgot that this is going to be the integer vector. So this virtual function would be used for the MSE error, the mean square error, and this for the cross-entropy. We need to create another virtual function that will return the derivative, the back propagation data, that could be constant and virtual, and the function that would return the loss that we have talked before. So now what we have to do now is to create our two files. New item, a file that would be on the output file and would be called MSE. And another file we are going to create that is going to be called Cross-Entropy. That's all. Okay, so now we have to create our class. We include the eigen library, eigen core, the configuration, and we are going to create MSE. Sorry. It's going to inherit it from output. We have a problem. Okay, we have not included yet our files into our include file. So first the output, we include our MSE and our cross-entropy. Okay, that's all. Now we return to the MSE error, and as we have done before, we I don't know why it's given this error, but wait. We write the derivative, a matrix in which we will store the derivative of our input with respect to the MSE error, and we are going to override our functions. First of all, the evaluate. We are going to evaluate. In this function, we are going to calculate the derivative. Prep layer data, the output, and the target data. The number of observations that we are calculating, number of observations, and the number of variables, nvar prep layer data dot rows. So the first thing that we are going to do is compute the derivative of the input layer, of the input of this layer. Okay, so the derivative of the input resize the number of variables, first of all, the number of rows, and the number of columns. Okay, and then we are going to do an operation, a normal operation, no alias operation, and as we have seen before, what? Okay. The derivative is the difference between those. Now we have done the difficult part. We override the matrix, the back propagation data, back prop. We have called backprop const, and we return the empty, and the function that will calculate the loss. As we have seen, the loss of the function is I don't know what happens here. Well, is the square norm, that is a function that is on the eigen and we divide it by the number of columns, important, and we multiply it by 0.5, as we have seen before. We don't have an error, but this is a little bit strange. Don't worry, we will continue, and we are going to do now the difficult part, the cross-entropy. The class cross-entropy that will heritage from output. Now it works. Output. What happens? This is strange. Don't worry. we include the eigen. We really don't have to include it, but I like to know the libraries that we are using in each file. We initialize the derivative, and now we can first of all override the evaluate. The evaluate, as we have seen, we have two different kind of evaluation. First of all, the matrix, and then the integer vector. Okay. And we are also going to define the matrix, the backprop, data, const, return, and bin. And we are going to start with the loss function because it is the easiest one. The result this is the number of elements in this matrix. We are going to define a pointer that will point to our data, and we are going to loop through it. That is really easy. If the data is greater than 0, our result will plus to std the log in base 10 of y. Okay. That's all. Okay. And we return the result divided by the number divided by the calls. Okay, because in each call we have a different training data, because we are doing the mini batch learning. So we compute a few training sets in each loop. So now what we have to do is calculate the derivative. And how we are going to do that? We are going to define the observations as we have done before, calls, and the number of rows. Bar. I'm going to copy this because it's the same for both. First, the derivative we are going to resize. Okay, don't go. And var and ops, and the derivative is an operation no alias, with no alias. That would be minus target. Remember that is a element-wise operation of pref layer data. Really easy, isn't it? And the next one is a little bit more complex. We are going to copy this to there. Set 0, otherwise we wouldn't have a matrix set to 0, and we are going to loop now in number of observations e++, and bin target. In this position we are going to do this layer data, and why we have done this? Because imagine we only want an output, one output, when we are computing, for example, digits, and we are computing the probability to get 0, 1, 2, 3, 4, 5, we only have a correct output. So if the output is a 6, the probability of every output have to be 0 instead of the number 6 that has to be 1. So that's why we have done this implementation with the integer vector, because in this kind of applications we don't want to compute and waste a lot of computer resources, so this would be much cheaper than doing the operation. So we have finished for now. I hope you like this video and you have learned the different kind of outputs and that we have to compute our error. And I think I would start recording more videos because in these few weeks I have been very busy and I couldn't do much for and record much videos for the channel. So I hope you like it. If you have a question, you can write me on the comment bar and I will answer as soon as possible. And in the next video we are going to see the different kind of optimizers, and we will be almost finished with our deep neural network library. So thank you for watching it and see you.